Hello and welcome back, marvelous AP Calculus AB students. We are back on the second part of our particle motion day. As we were going through last time, I realized that, wow, this lesson's going to be long, so I split it over 2 days. So day 81 was kind of that initial information about how integration works in with particle motion. We did a whole bunch of vocabulary and defining down here, especially how to manipulate that fundamental theorem of calculus. And then we started to work through 3 types of problems. All 3 problems give you something to do with velocity. This first problem gave you the graph of velocity. And we're going to do 2 more examples today. Our second example requires a graphing calculator, so make sure you have that ready, or if necessary, you can have Desmos out and ready to go. And then our last problem is going to present the velocity numerically through a table. Sometimes you hear this called tabular data. So let's get to it. Example 2. The rate of change, which we should know is our fancy name for the velocity or maybe the derivative in kilometers per hour of the altitude of a hot air balloon, is given by that equation over the time interval from 0 to 4, where t is measured in hours. Actually, in Reno, where I live, we have the hot air balloon races every year. It's very exciting. It's kind of early September, and yeah, they're up there for a few hours every morning. Very neat to watch. If you ever get the chance, go out and check it out. We are going to assume the balloon is initially 1 kilometer in the air. Now, there's a couple things to unpack here before we even start doing anything. The very first thing I want to look at is this equation. Because this is calculator active, the very first thing I want to do is probably graph that equation. Now, regardless of the type of graphing calculator you have, we want to go through and get this graphed because we're going to be using that equation throughout today. And if it's already graphed, then you're only going to have to type the equation in once. So what I've done to set everything up is I already have this graphed over here on my Inspire. You can do the same on your 84. I also have it done on Desmos in case I need to fall back on that. The second thing I'm going to do is change the window a little bit. They told us we're only going from 0 to 4, so 0 to 4 along the x-axis. I'm going to go from 1 to 5. I always tend to go maybe 1 further in each direction. So let's look at that window really quickly, right? Menu, window, window settings, and I'm going to go from -1 tab down to 5 and then hit enter. All right, here is our graph over here, nothing too bad. We also might want to zoom out a bit just so we can kind of see the top of our graph here over at 4, but it's not really necessary, so I'll hold off on it from now. But you could always change your window and try some larger y values. You could find f of 4, and right, I could actually, maybe this is good to do, since this function is defined as f1 of x in bold, I can jump back over here and say, well, let's figure out what is f1 of 4, because that's going to give me the highest my graph is going to be, right? You can tell over here that at 4 it looks like the highest it's going to be is, it's actually 6. So 4 comma 6 is right about here. It's actually a little bit lower than this piece. This goes up to 6.65. So the highest my graph needs to go up to is 6. Easy enough. And I always do that on these calculator active free responses because we're going to be using this equation over and over again. And it's much quicker just to type in f1 of something than to have to retype this whole piece. The other part that I like to do when I set up these calculator active word problems, or even if it's not calculator active, is write out the 3 levels of equations we're dealing with. And I always include the units. So what does that look like? Well, they gave us the equation r of t. And we know the units of r of t. T is, of course, time in hours, but they told us this is the rate of change in kilometers per hour. Because you are almost always given a velocity or a derivative equation, I like to go 1 below and 1 above. So 1 below means we take the derivative of r, which is going to be r prime. What are those units? Well, it's kilometers per hour, and hopefully at this point we're used to the idea that we are essentially dividing by another input or time unit, so we get kilometers per hour, or kilometers per hour squared. If I took the antiderivative, and I'll notate that as capital R of t, then our antiderivative is going to lose one of those units, and instead of kilometers per hour, we are just going to be back to kilometers. And maybe you could interpret this as our position, our velocity, and our acceleration. I like those units just so when we go through here and they say, what's r prime of 2? We already have those units, right? If they ask about what is the altitude, oh, that's a position, and so we know what we need to do. So let's go ahead and get started. For what values of t is the altitude of the balloon decreasing? Well, altitude is a position where it's located in the sky. So this is our position over here. Whenever you want to determine if an equation is increasing or decreasing, and altitude is capital R of t, if you want to see where something is increasing or decreasing, you take the derivative and you determine where the derivative in this case is negative. In fact, I'll make a full sign chart just so we get that idea. But yeah, essentially what I'm going to do here is take the derivative of R of t. Oh, that's exciting. It's lowercase r of t. And then we create a sign chart. So here's my quick sign chart for R of t. We are looking from 0 to 4. And to complete a sign chart, we need to determine where the derivative, where lowercase r of t equals 0. And it's probably a good idea to show that step on your paper, r of t equals 0, and then tell the reader what are those time values. Well, how do we solve this? Well, luckily, it's a graphing calculator active question, and we've already graphed this. Setting an equation equal to 0 is like finding its zeros on a graph. So if I look at my graph over here, I see 2 zeros of r of t, right? We're not looking for where the slope is 0. This is where r prime is 0. This is the graph of lowercase r of t, so let's find those zeros. Menu, analyze graph, 0. And my first 0 is over here. And then we'll do it one more time. Menu, analyze graph, 0. And my second 0 is over here. Hopefully we remember that those zeros are not accurate enough. We need to add on by hitting that plus to get more decimal places over there. Same thing with this guy. We're going to go through and give it a few more decimal places. And we have our zeros. 1.571. And the other one is 3.514. All right, so looking up here, we have 1.571 and 3.514, and those are where the graph of r of t is 0, or where the equation is equal to 0. How do we determine the signs of our sign chart? Well, the sign of an equation can be seen by looking at the graph and figuring out if the outputs are positive versus negative. It looks like my entire graph is positive before the first critical point, negative in between, and positive afterwards. So that's an easy fill. We know we are positive, negative, positive. Now, to answer this question, they just asked where is the altitude decreasing? Well, that's got to be where r of t is negative. So how do we state that? We say something like the altitude of the balloon is decreasing on, let's give that interval here, 1.571 to 3.514, because, and notice they didn't ask for a justification, so you probably could have left this off, but always a good idea to justify if it's just an extra couple words, because r of t is less than 0. R of t is negative, whatever sounds good to you. Just don't say because r of t is decreasing. Decreasing and negative are two different things. All right, 2. Find the value of r prime of 2 and explain the meaning of the answer in context of the problem. Indicate units of measure. Now, there are two ways to do this problem. There is the longer way and the shorter way. The longer way is you actually find this derivative, right? You find r prime of t, and I have every confidence that you can take the derivative of that equation. It's not terrible. But the faster way is because you have to take the derivative and then substitute into and then plug that into your calculator, why not just have your calculator do everything for you? We learned how to take the derivative last semester, so no reason to spend too long on this. Menu, calculus, and then derivative at a point, number 2. If you're on that Inspire, right, it's menu and then n deriv. I think it's menu 8 something, or math 8, something like that. X is fine because that's how I defined my function, and we needed to substitute in 2. Great. What do we want to take the derivative of? Well, I called my equation f1 of x. This will find the derivative of lowercase r of t and then substitute in 2, and it gives us an answer of -4. All right, so in a normal situation, you would have had to show what r prime of t equals, but because this is calculator active, it is expected that you will do derivatives on your calculator, and so we can just skip straight to r prime of 2 equals -4. What are my units? Oh look, we set this up ahead of time. This is kilometers per hour per hour. And I always like to think of this as over 1, so that in terms of the interpretation, every 1 hour we lose 4 kilometers per hour. This is showing us how our kilometers an hour, how our rate of change is changing. Okay, so how do we actually state this? Well, there are many different ways. I don't think I have a perfect explanation that works every single time, but we would look at this. At t equals 2, and you can put hours there if you would like, because derivatives always are an exact, specific, instantaneous rate of change. They are at something. So at t equals 2, maybe we'll say r of t, which is our rate of change, is changing, right? Is changing is probably the best way to go here, by -4 kilometers per hour per hour, right? The derivative always measures the rate of change of the original equation you start with. We start here with r of t, we find r prime, so we're measuring the rate of change of r of t. We're measuring the rate of change of the rate of change. All right. What is the altitude of the balloon when it's closest to the ground during the time interval 2 to 4? Oof, there's actually a lot to this question, a lot. So maybe it would help us to think about our sign chart again. This could, I think we could probably even do it a little bit quicker this way. They want to know the altitude when it's closest to the ground. So closest to the ground, I think we could probably interpret that as the minimum altitude, or the absolute minimum. And I think our absolute minimum here can be found by the candidates test. It goes pretty quickly, actually. So we're going to have to find the altitude at 2, at 4, and are there any critical points here? Oh, there are. 3.514, right? We saw that in our sign chart earlier. So let's do t and capital R of t, which is going to be the altitude. We'll need to check 2. We'll need to check the critical point, 3.514, and we also need to check 4. But then we have a bit of an issue. And the bit of the issue is we don't have an equation for r of t. How do we find, or capital R, how do we find the altitude at each of those values? Well, the only way you're going to be able to is if they give us an initial condition, if they tell us something about altitude somewhere in our problem. Well, they certainly don't on 3, but if we go back up to the beginning, I think they tell us that the balloon is initially 1 kilometer in the air. And so the way we'd interpret that is capital R of 1, initially, capital R of 0, so initially at a time of 0, we are 1 kilometer in the air. And that is very important. R of 0, and we want to find R of 2, and then R of this, and then R of that. So you're probably going to have to write a little small here, but that's okay. So let's work with just R of 2 first. And remember, we know that R of 0 is 1, and we want to find R of 2. Well, we can set this up with the fundamental theorem of calculus. We can say the integral from 0 to 2, right, our two inputs that are right here, of lowercase r of t, dt, is found through the fundamental theorem to be capital R of 2 minus capital R of 0. And manipulating this just a little bit, we are looking for R of 2 in this situation, so we add R of 0 over to the other side. R of 2 equals R of 0 plus the integral from 0 to 2 of R of t dt. Can we find these? Well, I hope so, because we know R of 0 is 1. That's our initial height when we start measuring or checking out the balloons. And then how do we find this guy? Well, this is just an integral of lowercase r of t. And again, there's two ways to do this. The long way around is you do this by hand, right? 1/4 t to the 4th minus 4/3 t cubed, so on and so forth. But this is calculator active. Let's make the calculator do the work for us. 0 to 2. So we jump back here, menu, calculus, integral, we're going from 0 to 2 of, and I called my equation f1 of x dx. Great. I got 16 thirds, and then if we wanted to add 1 to that, just so we have that in the future, answer plus 1, 19 thirds. So showing those two steps, we have 16 thirds, which is 19 thirds. Great, easy enough. So we found that the output here is 19 thirds, and this is in terms of kilometers. Well, you might say, isn't that a lot of work if we have to do this 2 more times? And normally, you'd be right. However, can we see what's going to change about this? If I just started over here and I'm going to do the next one, 3.514, nah, let's do 4 next. If I wanted to find the height at 4, well, it's going to follow the exact same formula. It's r of 0 plus the integral from 0 to 4 of r of t dt. And do we see why it's that formula every time? This is the initial height, and then this is the displacement. This is measuring how far away we end up from where we started. So we started at 1. After 2 hours, we're now 16 thirds to the right of 1. So where are we? Well, we're 1 plus 16 thirds. And so same thing here. R of 4 is the initial height plus how far we've moved. The initial height is still 1. And then for this guy, from 0 to 4, I'm going to be as efficient as I can. It's the nice person's word for lazy, right? We're going to copy this down if I can hit the right button, and then we're going to change this to 4. There we go. 8 thirds this time, and then just to do the rest of the math, even though it's just adding 3, 8 thirds and then 11 thirds. So we are at 8 thirds, and that brings us to 11 thirds. Okay. Now, this last one is a bit of an interesting conundrum because we don't actually want to substitute in 3.514 into our integral, right? 3.514, the height there is going to be found by r of 0 plus the integral from 0 to 3.514 r of t dt. I don't quite want to do this because this is not the exact height. We had to round, or I truncated, I stopped writing after 3 decimals. We want to use as an exact a value as possible. And so you might be saying, well, wait, does that mean when we look back on this graph, I have to write down this whole decimal? Well, no, all of your calculators, and we talked about this last semester too, all of your calculators have a way to store this value. So to do that, we hover over and we click once. And I don't think that worked well on mine. I'm going to try that again. There we go. We click 1 time. Perfect. And then once you've clicked, control and then store, right? I access the STO, the store function. It says, what variable do you want to store this x coordinate as? I'm going to store it as b, and then enter. So this is now stored, and if you hover over it, it says it's linked as b. So what does that mean then? Well, it means that A, if you wanted, you could call this number, we could say that this number is equal to b, and I usually put a couple periods after, just so an ellipses, just so you know it goes on forever. And then when you do this on your math, you can just say r of b and r of b, so that way you don't have to write out the whole thing. Now, can you? Of course, you can say 3.514, put a couple dots after to show you're plugging in as accurate a decimal as possible. Okay, and then as we finish this off, 1 plus, well, let's jump back to our calculator here, and we are going to do the integral from 0 to b this time. And notice when I type in, oops, I'm going to delete the entire integral, so we're just trying again. There we go. Calculus integral from 0. You'll notice when I type in b, it turns bold. And that's because it's stored as some value, or some value is stored as b. And then my function is still f1 of x dx. Perfect, and enter. 1.3480 something. 1.480 something. Yeah, there we go. Now you might say, well, wait, that decimal looks rounded too. Did it actually use the whole thing? But if you hit enter on it, you can see that it is actually a very accurate decimal there. Okay, and then if you add 1 to that, I assume you can do the math in your head, right? It's going to be 2.3480, so on and so forth. Now, do you have to do that? Yes, you do. And the reason you have to do that is because if this decimal is off by too far, and then you do lots of calculations with it, then this decimal is going to be off even further. And if your final answer is off from the exact value out to 3 decimal places, you miss the point for the final answer. And you don't want to miss any points if at all possible. So we do want to be as accurate as possible. 2.348 something. Great. Now, can we answer this question? Well, the whole idea of the candidates test is you test the endpoints. We did that. And you test any critical points. And we saw if here is 2 and here is 4, there's only one critical point there. If you just drew the graph from here, our altitude decreases and then increases. We probably could have seen that this is going to be the spot with the lowest altitude, but I thought it was nice to remind us of the candidates test. And so once we've done that, once we found these 3, what's the altitude of the balloon when it's closest to the ground? We would just say something like the lowest altitude. Nothing bad at all, right? That is our justification for our work, and we're good. Alrighty. Find the value from 0 to 4 r of t dt. Oh, this is so exciting. We already did this. Look how awesome we are. The value from 0 to 4 r of t dt is up here, equals 8/3. Explain the meaning of the answer. Well, this is technically in kilometers, right? And that is the displacement of our particle, right? This tells us that at a time of 4, and I should say the balloon is 8/3 kilometers above, right? Because this is positive, we're talking up and down, above its position. Now we shouldn't use its. I think people will cringe. Above the balloon's position at a time of 0, right? So we don't actually know by this 8/3 where the balloon is. We just know that at a time of 4, it's 8/3 kilometers above where it was at a time of 0. Now, we know that at a time of 0, it was at 1, and so by adding 8/3, we can figure out where it was at a time of 4, but interpreting these integrals can be tricky, so the more we try, the better we're going to be. All right, find the value of the integral from 0 to 4 of the absolute value of r of t. Okay, well this one's going to be a little trickier. We're going to need to throw some absolute value around this guy. I wonder if that'll change anything. Well, to get a visual to see if it changes anything, let's look at the graph. Our graph over here, we're going from 0 to 4. If we apply absolute value to this graph, will it change? Well, yeah, this negative piece down here will flip up, and it'll kind of come down, go back up, and then continue going up. Because what happens when you measure the altitude or the integral, the area of this graph from 0 to 4, well, let's see if we can take a journey. We are adding on positive area. So from 0 to this first 1.571, our balloon is going up, 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 up until it gets here. And then we're gaining negative area. Maybe we're losing area, which means we're losing altitude. So we go up, 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 up. Now we go down, 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 and then we go up a little bit more. Because these two almost cancel each other out, if we make everything positive, now we're just going to add up the 3 areas. We're going to add up the amount we went up, we'll continue to add the amount we went down, and then we'll finish by adding the amount that we went up at the end. Right? So what does that give us? This gives us our total distance traveled. Can we do this on the calculator? Certainly. Menu, integral from 0 to 4 of, we need to do the absolute value first. You'll actually notice absolute values on this button right here. It's next to the 9. I call it our quick key button. If you're on the 84, you want to go to math and then to the right to num and um, and you'll see absolute value is your first option. Absolute value is up here, absolute value of f1 of x, and then we of course have dx. Now the calculator almost always gives you an error on this because it has trouble applying absolute value. You can just ignore that, and we can maybe do a separate video of why the error comes up, but I got 11.528. units, kilometers. Well, this value is really different than this one, right? 8/3, in case you're curious, is 2.666 repeating versus that one. Well, that's because we didn't cancel out that middle negative area. So what is this? This is the balloon travels 11.528 total kilometers from t equals 0 to t equals 4. Right? We're not canceling it out. How does it travel those kilometers? Well, thinking of those three areas, first it goes up a distance, then it goes down a distance, then it goes back up, and we just added those three up to get 11.528. This value should always be greater than or equal to the displacement. It would be equal to the displacement if there's no negative area, but usually there is negative area in these situations, so it should almost always be bigger. If you ever get a number that's smaller than this, you did something wrong. What's the maximum altitude of the balloon during the time interval 0 to 4? Oh, this one you're saying, oh my gosh, this sounds awful, because you see maximum altitude and you're like, oh my gosh, the maximum altitude, this is an absolute max, absolute min question. It's another candidates test, and yeah, you're right, but we've already done most of it. So we're going to look at time values, and we're going to look at the altitude, capital R of t. We know we have to test 0. We know we have to test 4, and then we have to test any critical points on the way through. Critical points, we did that up above. There's two of them, 1.571 and 3.514. 0.571 and 3.514. I'll put the little dots after so we know they go forever. But guess what? We've done almost all of these. We already found R of 4, that's 11/3. We found R of 3.514, that's 2.348. And we know R of 0, that's given to us, that's 1. I think there's only one more of these that we have to do, which is super exciting, right? To do this one, all we do is we do that same function. We're going to say R of 1.571 dot dot dot. It's going to be where the balloon started plus the integral from 0 to 1.571 of R of t dt. And we can take care of all of that on our calculator, but I do want the most accurate value of 1.571 whatever, so I'm going to jump back to my graph. I'm going to practice clicking once, and then Control Store. I'll store this one as A. Why not? If you do, by the way, ever get an error when you try and store it, it's probably because that variable is already used. If you try to use A and it's already stored as something else, it'll be like, error, just use a different variable. If you want to get rid of the stored variables, you just go to Menu, Actions, and then clear A to Z. That'll clear out any stored variables from A to Z. That's never a bad idea to do before a test, so you don't get tripped up on that. I'm not going to do it now, though, because I don't need to. So, calculus, and it would destroy the storage that I just did. All right, sorry about that bell. Still recording this at school. So integral from 0 to a this time, and we're down to f1 of x dx. There we go, 5.779. Good, and I assume we can add 1 to this, 6.779. Alright, now the results of this shouldn't have been too much of a surprise, because looking at our sign chart again, we can see that the balloon will increase in altitude, and then decrease, and then increase. So really there's only two possible spots where the balloon is at its highest point, either this guy or the end point. And you could have even estimated it based on the graph over here, though this one would be pretty tricky, right? The balloon started at 0, 1, and then we increased area. So it goes up, 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 up to here. And then we lose almost the same amount of area, and then you go up just a little bit. So to me, if you go up a lot, this point's going to be probably our tallest, because then we pretty much lose all of it. We're back down to 1, and then we only go up a little. But that's not very, I don't know, technical here. So either way, I think we can come up then with our maximum altitude here. I'll put some kilometers at the end, maximum altitude. Our justification is the candidate's test, and we are good to go. Now that we've finished our calculator algebraic approach to our real-world problems for particle motion, we're going to go ahead and move on to our last question, which is presented in a tabular or numerical manner, and we'll see what we're doing here. So, gives values for velocity and acceleration. A particle is moving along the x-axis. Velocity and acceleration are differentiable functions, right? So that means that they are both continuous as well. That'll probably come into play shortly. The velocity is decreasing for all values. Okay, and decreasing, I think, means the acceleration is negative, right? Because acceleration is the derivative of velocity. Use the data in the table to answer a few questions. Well, the first thing I like to do is I like to write out my 3 layers or levels of equations. We already have the velocity right here, and we know that the derivative of velocity is acceleration. But what about the antiderivative of velocity moving up above? Well, because we're moving along the x-axis, I'm going to call that x of t. So the derivative of x of t is velocity, the derivative of velocity is acceleration. They also didn't give us any units, so maybe that's a yay for us. We don't have to keep track of those. So let's begin. Is there a time t when the particle is at rest? Well, at rest means the velocity is 0. It means the particle has no speed, it's not moving. So let's look at velocity, and as we look through here, you might notice that there are no velocity values of 0. However, you might also notice that the velocity goes from a speed of 5 to a speed of 3 to a speed of 1, right? So we're going, or maybe we think of it this way, the particle's moving to the right, and now the particle's moving to the left. Well, if you think about something that's moving to the right, it's going this way, before it can start moving to the left, what does it have to do? Well, it has to stop. Another way, maybe a little bit more numerically to think about this, is we went from 5 to 3 over these first 2 time values. Well, you'd have to go from 5 to 4.9 to 4.8 to 4.7 all the way down to 3, and then 3 you'd have to go all the way down to -1, and I feel like to go from 3 to -1 you'd have to cross over 0, wouldn't you, somewhere in there? Now, isn't there some sort of theorem that tells us that if you start at one y value and end up at another, that you have to cross over all the intermediate y values? How about the intermediate value theorem, the IVT? So how does this work? Well, I would say something like, yes, we always want to make sure we answer the question, right? And now we can pick 2 points. You can use the end points here, because 0 is certainly between 5 and -8. You can shrink the interval, and you can use the end points here. And since I circled those last, that's what I'll use, right? As f of, as v of 2 equals 3, and v of 6 equals -1, and this is going to be a huge run-on sentence, so I apologize for that, and 0 is between these two, isn't it, right? V of 6 is the smallest, then 0, then V of 2, right? 0 is in between -1 and 3, and, like I said, run-on sentence. What do we need in order to use the IVT? Oh, V of t has to be continuous, doesn't it? But where does it say V of t is continuous? Well, it doesn't. And so the AP exam does expect you to make the jump from differentiability to continuity by stating it. You can't just say, and V of t is continuous, because the readers are going to say, how'd you know that? They want to make sure you didn't just memorize the definition for the IVT. And the way we know that is because it tells us V is differentiable. So, and because V of t is differentiable, and therefore continuous, the IVT guarantees a time t such that, and I'm just going to say t occurs somewhere between 2 and 6, doesn't it, right? 2 less than t less than 6, where the particle is at rest. And if you wanted to explain, you knew what at rest was, you could say where V of t equals 0. lots of pieces there. Definitely writing those theorems can be tough. Usually theorem questions are worth 2 points. So as long as you showed some sort of setup and got the differentiability and continuity, you're doing great. And then the conclusion is usually that second point. All right. At what time indicated in the table is the speed of the particle decreasing? Well, we need to remember that speed decreases when velocity and acceleration have opposite signs. So let's just look at all the signs of velocity and acceleration. Are these signs opposite? Well, no, 5 is positive and 0 is without sign. 0 is neither positive nor negative. All right, this one, we are moving to the right at a speed of 3, but we are accelerating to the left at an acceleration of 1. So those are opposite signs. Here we have the same sign. We're moving to the left at a speed of 1, and we're accelerating to the left at an acceleration of 3. That is speeding up, and so is this. So where is this particle decreasing in speed? We would say at t equals 2, the particle's speed is decreasing because the signs of v of 2 and a of 2 are opposite. Now be very careful on this type of problem, opposite. Sometimes I'll have people say the speed is decreasing because, and then they'll say v of 2 equals 3 and v of 2 equals negative, and a of 2 equals negative 1. And that is essentially the why, but I'm never quite sure if the AP exam would accept that because you didn't actually explain why. You just said, here are those two. And that doesn't necessarily tell me that you know what you're looking for is the fact that they are opposite in sign. So I think it's really important that you mention the values are opposite in sign, maybe in addition or, as an alternative to just stating what the values are. All right, use a left Riemann sum to approximate from 0 to 10 of v of t dt, show the computation, cool, and then explain the meaning of the definite integral. All right, so left Riemann sum. We're going to start with the integral, 0 to 10 v of t dt, right? We're summing up a base and a height, so let's get some bases and some heights in here. So we're going from 0 to 10, and we have 1, 2, 3 subintervals here. My first subinterval from 0 to 2 has a base of 2. And the height, we're doing v of t here, right? So we have two options as a height. This is a left Riemann sum, so we're excluding the far right, and we choose the left value, so a height of 5. My next Riemann sum has a base of, from 2 to 6, has a base of 4 and a height of 3. And then my last Riemann sum has a base of, from 6 to 10 is 4, and a height of negative 1. That looks pretty decent. Let's finish this out. So we have 10 plus 12 minus 4. 22 minus 4 is 18. What does this actually mean? Well, the antiderivative of v is x of t, its position, and essentially what this is finding is the position of the particle at 10 minus the position of the particle at 0. And so we should realize that this is how far apart the particle is at these two times, or the displacement. So how do we write this? At t equals 10, the particle is 18 units to the right of the, and notice I always try to avoid it, right? I erased that earlier, of the particles instead of its, of the particle's position at t equals 0. So it doesn't tell us where it started, it doesn't tell us where the particle ended up, it just tells us that it is 18 units further to the right of where it started. You could also work the word displacement in there. The particle has been displaced by 18 units, that would be fine, but I find this sentence works out pretty well. Okay, is my approximation in part 3 greater than or less than the actual value? Well, what do I know about the function v of t? I think that's going to help us. Velocity is decreasing for all values of t. Okay, so if velocity is decreasing for all values of t, this one's a little bit trickier, I think, here, because we do get some negative values, but let's just kind of do a nice decreasing graph like so. And if I split this into maybe like, I don't know, a few subintervals here, something like this, let's take a peek. We did a left Riemann sum, left Riemann sum, left Riemann sum, and a left Riemann sum. I think this one's going to be a little bit trickier because we have both above and below here. So we're not quite sure because velocity isn't positive the entire way through. Now, because the majority is positive, then I would probably conclude that, yeah, this is going to be an overestimation, right? See how much extra we overestimated versus this little piece that we underestimated here, because there's only technically 3 of these. So my guess is it's an overestimation, but I would also guess that when I made this problem, I wasn't thinking about this, so that's a little bit awkward, but that's fine. I think it's important to acknowledge our faults, and I don't think that there's probably a great answer to this. But the idea is the same. If you want to find if an approximation is greater than or less than, you create a sample graph. I did a decreasing graph. Normally our decreasing graph would just be above the x-axis. You subdivided a bit. We did a left Riemann sum, and clearly that is an over approximation. But for this one, I'd probably say, oh, Mr. Grant messed up. There's no good answer. All right, let's move on to 5. Approximate the value of the integral of the absolute value of v of t dt using a trapezoidal approximation with the 3 subintervals indicated by the values in the table. Show the computations. Explain the meaning. Okay, well, this one's not bad. We've already done a lot of the groundwork here, but we want the absolute value this time, and we're doing a trapezoidal. So jumping back up here, if we're doing the absolute value of velocity, all that means is that all of the outputs are positive. How do we do a trapezoidal? And I think a lot of people, it will help you to graph these points, 0, 5, 2, 3, 6, 1, and 10, 8. And I'm actually going to take my advice here and graph this. I just think visually it's a little bit easier for people, and I'm actually going to take my little mistake up here and graph it in this spot, because why not? So x values 0, 2, 6, and 10. So here's 2, here's 6, and here's 10. Y values, I have 5, 3, 1, 8. So 1, 3, 5, 8. Okay, and then we'll graph those points. 0, 5, 2, 3. 0, 5, 2, 3. 6, 1, 10, 8. And now we're going to make trapezoids, right? Visually, these trapezoids are so much easier to see than just trying to picture them in your head. However, some of you might be really good at that, and that is awesome. I have no complaints. But just for all of our learners that struggle with a little bit more of this visualization, creating a graph isn't bad. What did that take me? 30 seconds? Let's do trapezoids. Okay, our trapezoids, we'll do the orange one first, are always the average of the 2 bases, and the bases are the parallel sides here. So my first base is 5, and my second base is 3. That's the average of the bases. That gets me a base. Then we need to multiply by the height, which is 2. All right, next trapezoid, we have 1/2. The first base is 3, the second base is 1, and then the base is 4. And then last but not least, we have a 1/2. Base is 1, base is 8, and then the actual base is 4, but that's really the height. So we're right here. Cleaning this up a little bit further, those cancel. This becomes a 2. That becomes a 2 as well. So we get 5 plus 3, which is 8. And then 4 times 2 is 8. And then 9 times 2 is 18. So we have 16 and 18, which is 34. Explain the meaning of our definite integral. Well, at this point, hopefully we remember that by finding the absolute value of velocity and then integrating, we are finding the total distance traveled. So the particle travels 34 total units from t equals 0 to t equals 10. Last but not least, determine the value of 0 to 10 of a of t dt, explain the meaning. Well, looking at this, you might say, well, wait, they didn't tell us what type of Riemann sum to do. How do we evaluate that? Well, you're thinking too hard, because there are two ways to evaluate any definite integral. One way is to use the area under a graph, which is what we've done so far today. But the other way is the fundamental theorem of calculus, isn't it? Can't we say from 0 to 10 a of t dt is equal to, let's do it like this, v of t from 0 to 10. So it's just v of 10 minus v of 0. And we can even evaluate those using the table, right? V of 10, I should get rid of my negatives here. V of 10 is negative 8, and V of 0 is 5. So we have negative 8 minus 5, which equals negative 13. Now, you might be saying, well, wait, if it's that easy, why did I do all those Riemann sums before? Well, let's look back at this guy. If you wanted to apply that here and say from 0 to 10 of V of t dt, then certainly the antiderivative would be the position function, and then we would substitute these into the position function. And this answer should be probably somewhat close to the answer I got down here. Well, how do we find that answer? Well, we look up to the table and, oh, they didn't give us any values for x of t. So if we don't have the antiderivative, then we can't substitute values in, and so we have to do the area process that we did before. They will always tell you what kind of Riemann sum to use. Finishing this off, they said explain the meaning. Well, we subtracted two velocity values, and that tells us the difference between them, right? So what does this mean? We would say the velocity, I always like to start at the ending value, at t equals 10 is negative 13 units, whatever the units would be, right? And we don't want to say smaller, because negative and smaller is kind of a double negative, and that's never good. So we would maybe say, you could either say 13 units smaller, or negative 13 units different from the velocity at t equals 0. And that's that. Now, we really went through every kind of particle motion problem that you could expect, graphically, numerically, algebraically. The AP exam will still find different ways to throw these at you, and we will practice more free responses in the future. But really hold on to this packet. I think you'll find that you can reference pretty much everything we do the rest of the semester with regards to particle motion in this packet. You also might want to dig out yours from topic 4, maybe rewatch those videos too to make sure you're very confident on this, because particle motion comes up all the time. There is quite often a full free response on particle motion. It's been very common the last few years, and there are always a few multiple choice questions. At this point, you're able to do all of those style of questions too. So if you wanted to start working back through free responses, find all the particle motion ones and do them all. You're going to find one almost every year. You can do every part about it. You're that good at calculus at this point. Try them. Please let me know if I made any mistakes, and I'm excited to have you back for our next class, day 83.